Do you live in Sicily? Do you live in Catania, in Randazzo, in Zafferana Etnea, or anywhere in the shadow of the largest volcano in Italy? Do you have a trip planned to the slopes of Europe's most active mountain in the coming months? If the answer is yes, you need to watch this full video because scientists have just confirmed something about the volcano towering over your home that nobody fully understood until now. And it changes the way we have to think about why Mount Etna behaves the way it does. For more than 2,000 years, people living on the eastern coast of Sicily have watched Mount Etna erupt again and again, more frequently than almost any other volcano on the planet. The Smithsonian's Global Volcanism program has documented its eruptions going back to 1500 BCE, one of the longest continuous volcanic records anywhere on Earth. In the past 10,000 years alone, Etna has produced at least 197 confirmed eruptions. It rises more than 3,000 meters above the sea, towering over the city of Catania and the fertile farmland that surrounds it, farmland that exists precisely because of the volcanic soil this mountain has been depositing for 500,000 years. But here is the problem that has quietly frustrated volcanologists for decades. Despite Etna being one of the most intensely studied and most densely monitored volcanoes on Earth, with over 50 seismometers, GPS stations, gas sensors, and round-the-clock camera coverage from Italy's National Institute of Geophysics and Volcanology, scientists never actually had a satisfying explanation for why Etna exists in the first place, or why it behaves the way it does. This next part matters, because volcanoes do not form randomly. For decades, geologists have organized nearly every volcano on the planet into 3 categories. The first forms at tectonic plate boundaries, where plates pull apart and allow mantle material to rise and melt, building new ocean floor along mid-ocean ridges. The second forms in subduction zones, where one tectonic plate slides beneath another, and water carried down with the descending plate lowers the melting point of the mantle above it, often producing explosive volcanoes like Mount Fuji in Japan. The third forms in the middle of tectonic plates entirely, where unusually hot material rises from deep within the mantle in what is known as a hotspot, the mechanism responsible for volcanic island chains like Hawaii. Mount Etna sits right at the boundary where the African plate is sliding beneath the Eurasian plate, which should make it a textbook subduction zone volcano. But its chemistry has never matched that story. Etna's lava carries a chemical signature that looks far more like a hotspot volcano, the kind of volcano you would expect to find in the middle of an ocean, not perched directly on top of a colliding plate boundary. For decades, this contradiction simply did not have an answer. Most people are missing how strange this gap in scientific understanding really was, given how closely this mountain is watched. So a team of researchers from the University of Lausanne, working alongside scientists from Italy's INGV observatory in Catania, set out to finally solve it. Their approach was methodical. They collected rock samples from Mount Etna spanning the volcano's entire 500,000-year eruptive history and used geochemical analysis and experimental modeling to reconstruct exactly how the chemistry of its lava has changed, or in this case, has not changed, over that enormous span of time. Their results, published in April of 2026 in the Journal of Geophysical Research, Solid Earth, revealed something the team did not fully expect. The chemical composition of Etna's magma has remained largely consistent across its entire 500,000-year lifetime, even as the surrounding tectonic regime around Sicily continued shifting and evolving. That kind of long-term chemical stability simply does not fit the conventional model where magma forms fresh, shortly before each individual eruption, churned up locally by heat and pressure in the moment. Instead, it pointed towards something almost the opposite. The magma feeding Etna was not being newly created. It was already sitting there, deep underground, long before it ever made its way to the surface. Here is why this is serious for how we understand this volcano going forward. According to the research team, Etna is fed by small pockets of magma that already exist roughly 80 kilometers beneath the surface, sitting within a layer of the Earth known as the low-velocity zone, a region identified through seismic and electrical anomalies at the boundary between the rigid lithosphere and the more pliable asthenosphere underneath it. Rather than forming through fresh melting tide directly to the act of subduction, these pre-existing pockets of melt get squeezed upward sporadically, transported toward the surface by the complex tectonic flexing produced as the African plate bends and grinds beneath the Eurasian plate near Sicily. Lead researcher Sébastien Pillet and his colleagues describe the mechanism using a vivid, simple image that gives the volcano its now widely repeated nickname, magma being squeezed out through fractures in the bending tectonic plate, much like liquid being squeezed from a sponge, or, in the words used by multiple outlets covering this study, like fluid escaping through a leaking pipe. One more thing you need to know. This mechanism is not entirely unprecedented on Earth, but it is exceptionally rare and almost never observed on this scale or on land. Scientists have previously documented a similar process at tiny submarine volcanoes called petit spot volcanoes, First identified and described by Japanese geologists back in 2006, petit spots are small underwater volcanic features that form when pre-existing pockets of melt, trapped at that same lithosphere-asthenosphere boundary, get released through plate flexure, the gentle bending of oceanic plates as they approach subduction zones. Until this new study, petit spots had only ever been documented as small submarine features, modest in size and largely overlooked outside of specialist research circles. Mount Etna, according to this new research, may represent something genuinely unprecedented. The first known instance of this exact petit spot mechanism scaling up to build an enormous, persistently active stratovolcano on land, one capable of becoming the largest and most voluminous volcanic edifice in all of Italy. This is where it becomes dangerous to oversimplify what this discovery actually means, and most coverage racing to call this volcano a leaking pipe risks missing the real significance. This is not a plumbing metaphor about Etna suddenly becoming more hazardous or more unstable than before. What the research team is describing is a previously unrecognized fourth category of volcanism altogether, sitting outside the three traditional mechanisms geologists have relied on for generations. As one of the researchers explained to Live Science, the lithosphere itself, the rigid outer shell of the Earth that we tend to think of as geologically passive, may actually play a far more active role in feeding volcanic activity across the planet than scientists previously assumed, and not just at Etna. If pre-existing melt pockets trapped at this boundary layer can be squeezed loose by plate flexure in Sicily, the same underlying mechanism could potentially explain unusual volcanic behavior at other sites around the world that have similarly defied the traditional three-category system. Now the focus shifts to what this means for predicting Etna's future behavior, which is the part that actually matters most for the people living on its slopes. The study suggests that variations in Etna's eruptive volume over its half-million-year history have been primarily controlled by plate movements themselves, the physical bending and flexing of the crust around Sicily, rather than by fluctuations in how much fresh magma happens to be generated at any given time. In simpler terms, the supply of magma sitting in that deep reservoir has remained relatively steady and available. What changes, what actually determines how much lava reaches the surface and when, is how hard the tectonic plate squeezes that underground sponge. This reframes decades of monitoring data collected by INGV, suggesting that some of the deep tectonic stress signals scientists already track around Sicily may carry more direct predictive value for Etna's eruptive timing than previously understood, a genuinely useful refinement for the volcanic hazard models researchers at INGV use every single day. And now, while this research has been unfolding in scientific journals over the past several months, Etna itself has continued doing exactly what Etna always does, erupting. The most recent activity began on January 1st, 2026, when a new eruptive phase opened a fissure vent at roughly 2,000 to 2,100 meters elevation inside the Valle del Bove, the massive 5 by 10 kilometer caldera carved into Etna's eastern flank. Lava rivers descended steeply toward the villages of Milo and Fornazzo, advancing to within roughly 5 kilometers of both communities before the activity eased, close enough to generate dramatic footage and real public concern, even as INGV confirmed no immediate threat to residential areas. That eruptive phase continued through mid-January with gas emissions and cooling lava flows persisting in the Valle del Bove through at least January 18th. Then, in early June, Etna stirred again. On June 14th, INGV's Catania Observatory reported minor eruptive activity beginning at Etna's summit craters, prompting aviation authorities to raise the Volcano Observatory notice to aviation alert to yellow. By June 15th, diffuse ash emissions had pushed that alert level higher still, to orange, though officials confirmed ashfall remained confined to the immediate summit area. Minor ash emissions continued through at least June 17th. Then, in the most recent reporting window covering June 16th through 22nd, INGV documented explosive activity strengthening at the southeast crater, with intense strombolian explosions and a lava overflow that descended Etna's flanks, curving northeast and then east. The resulting eruption plume rose 6 to 7 kilometers above sea level, drifting north and depositing ash as far away as Randazzo, 15 kilometers from the summit, and even reaching Gioiosa Marea, 46 kilometers to the north. The lava flow from this event advanced to an elevation of 1,130 meters and stretched 9 kilometers long, with intermittent incandescent flashes still visible at the northeast crater as recently as June 21st. But that is not the real story, not the whole story when you place it against the backdrop of Etna's full history. This kind of activity, summit explosions, modest ash plumes, contained lava flows confined largely to the upper slopes and the Valle del Bove, represents entirely typical behavior for this volcano. Local volcanologist Dr. Boris Benka, a familiar voice during past eruptive phases, has repeatedly cautioned residents and visitors against the kind of viral misinformation that tends to spread the moment dramatic lava footage circulates online. Footage that often makes flows appear far closer to villages than they actually are. As Benka has put it, living at the foot of a volcano that, if conditions turn genuinely severe, poses a serious threat to property roughly once every several decades, is statistically no more dangerous than living along a river that floods every year, or beneath an alpine slope prone to seasonal avalanches. Etna's frequent multiple times a year eruptions are simply this volcano's baseline behavior, the very behavior that, until this new study, scientists could not fully explain. The historical comparison worth remembering here goes back to 1669, Etna's most destructive eruption since antiquity. Lava flows that year destroyed at least 10 villages along the volcano's southern flank, before reaching the walls of Catania itself 5 weeks after the eruption began, eventually diverting into the harbor and filling it with rock. Contrary to widely repeated claims of massive loss of life, contemporaneous written accounts from that era recorded no deaths directly attributable to the lava itself, a detail historians have had to actively correct over the centuries, as exaggerated death tolls circulated. That distinction matters now more than ever in an age of instant video and, increasingly, AI-generated misinformation, where a slow-moving, well-monitored lava flow can be made to look like an unfolding catastrophe to anyone scrolling past a dramatic clip without context. Most people are missing just how good Etna's monitoring infrastructure actually is, which is precisely why this new leaking pipe research matters so much for the future. INGV's network includes more than 50 seismometers tracking the tremor and small earthquakes that typically precede eruptive activity. GPS stations, capable of detecting the ground swelling associated with magma movement beneath the surface, round-the-clock visible and infrared cameras providing constant coverage of the summit craters, dedicated gas monitoring equipment tracking sulfur dioxide and carbon dioxide output, and satellite instruments capable of detecting thermal anomalies and ash plumes from orbit. This is, by any measure, one of the best instrumented volcanoes on the planet. What this new study adds is not another sensor or another data stream, but a fundamentally better theoretical framework for interpreting everything those instruments are already recording, a clearer understanding of where Etna's magma is actually coming from, and what physically triggers its release. One more thing you need to know about why researchers are calling this discovery potentially significant well beyond Sicily itself. If the lithosphere, the rigid outer shell of our planet long treated as a largely passive backdrop to volcanic activity, can actively store and selectively release pre-existing pockets of magma through plate flexure, that mechanism is not necessarily unique to this one mountain. The research team has suggested that similar processes, similar leaking pipes hidden beneath other tectonically active regions around the world, may help explain other volcanoes that have likewise defied easy classification under the traditional three-category model that has guided volcanology for generations. Mount Etna, sitting at this rare and specific intersection of subduction zone geography and hotspot-like chemistry, may be one of the only places on Earth where scientists can directly study and sample the chemistry of this deep boundary layer simply by examining lava that has already reached the surface, without ever needing to drill 80 kilometers down to retrieve it themselves. The volcano towering over Catania tonight is doing exactly what it has done for 500,000 years, venting gas, producing minor ash, sending intermittent glow and strombolian bursts from its summit craters, all of it now monitored, not just by INGV's dense instrument network, but by a genuinely new scientific understanding of where that activity actually originates. The mystery that puzzled volcanologists for decades, why a volcano sitting on a subduction zone behaves chemically like a hotspot, has a real answer now, rooted in a hidden reservoir of ancient magma squeezed slowly upward through the bending plate beneath Sicily, exactly like fluid escaping a leaking pipe. We will know more as INGV continues its weekly bulletins, and as researchers apply this new framework to existing decades of monitoring data, but for now, Mount Etna's centuries-old mystery has finally been confirmed, and Europe's most active volcano has officially earned a place in a brand new category of its own.